If you're watching this video, that means the STAR test is just around the corner. What's up, guys? Mr. Martinez here. This is most likely going to be our last video. Today's objective is to remind y'all how to start your STAR test by showing you and walking you through how to mark up the periodic table and then how to use it as a tool to identify elements, their characteristics, their properties, things of that nature. Okay? It's only going to be about 4 or 5 slides. Let's get right into it. All right, guys, so the first thing that we want to do when you get your physical periodic table on test day, you're going to want to go ahead and divide the table up into its 3 sections by identifying the metalloids first. I gave you a little saying to help you remember that. It's kind of silly. Let's see if you remember it, and let's see if you know how to start the assessment. So the first thing you're going to want to do is find the black stair line, and let's go to the bottom of it, and you'll see P and you'll see T. And if you remember, I told you let's pretend that stands for periodic table, okay? Kind of self-explanatory, and it helps us out there. So we're going to go ahead and highlight these. Now you will get an actual highlighter and a physical representation of the periodic table with your reference materials on the big game day, okay? So periodic table should annoy. All right, so let's go ahead and highlight that. Periodic table should annoy, and we're following the black stair line. Periodic table should annoy grandma super, okay? Periodic table should annoy grandma super, and we're continuing on following that black stair line. B, bad. So periodic table should annoy grandma super bad boron, okay? And that's our last of the metalloids. If you remember correctly, the metalloids are the group of elements on the table that exert properties of metals and nonmetals. We most commonly refer to them as semiconductors because they semi-conduct electricity. Sometimes they conduct electricity only under certain conditions, or they conduct electricity but just not very well. Everything to the left of the metalloids has to be a metal, with the exception of hydrogen, which is a gas, but it is in column 1A because of its chemical properties, its reactivity, the way it behaves. It's very unstable. Everything to the right of the metalloids is what we would call a non-metal, okay? So those are your 3 main groups. That's how you start the STAR test. Now, the next thing that we're going to want to do is you'll take your pencil, and I'm going to use a red, basically, writing device here. You guys would use your pencil because that's the only other tool you're going to get. And let's identify the 2 most reactive families or columns. So the first thing we're going to want to do is go to column 1A and do our exploding unstable lines, right? This is our most reactive metal family. Well, why is it metal? Because it's to the left of the metalloids, okay? And if you remember, we call these the alkali metals, okay? So the alkali metals have 1 valence electron. That's why they're in column 1A. Yes, we included hydrogen in there. It's not a metal, but it reacts chemically the same way. Okay, very unstable. So we go ahead and line it up with the rest. Now, which other group would be the most reactive, but in the non-metal side, which would be to the right of the metalloids? Well, you got to think of the magic number. The magic number is 8. So you want to have 2 groups that if you combine them, if you add them together, their numbers of the column, they're going to equal 8. So it can't be 8 because 8 is already stable, right? So 1 plus blank will give us 8. So if we go in here and we look and you remember, it's 7A. So 7A, okay, plus 1A, when they combined, 7 plus 1, it gives us a full valence shell. A full shell means you have 8. And when you have 8, you're stable, you're chill, you're non-reactive, and you don't have any type of, explosive chemical properties. So the name of the family for 7A, if you remember, is our halogens or halogens. Okay, so halogens and alkali metals go together. 1 plus 7 will equal a stable 8. They help each other out. It's kind of like Romeo and Juliet on opposite sides of the table. They're not supposed to interact, but when they do get together, it's peaceful and they complete each other and they're stable. So that brings us to 8A. I want everyone to go to group 18 or 8A. You're going to draw a circle above it and put an X over that. Okay, why are we putting that? Well, because the magic number is always 8 in the valence shell. So when you have 8, you have a chemically stable element or atom. So that means you are non-reactive. So what we call these guys, let me grab my highlighter. What we call these guys is, actually, you know what? Let me go back to this. Okay, I'm going to write it here, but you can write it on the side. I can't turn the screen. You're going to write, we call these guys the noble gases. You can write it going down this way if you want to. The noble gases have a full valence shell, like I said. They do not react. Think of the NO. Go ahead and underline that. NO means no reaction. And the other name that you need to be familiar with for this family is inert, because they are also known as the inert gases. If they say an element is inert, they're referring to the noble gases. Back in the day, none of those elements bonded or reacted with any other element under any condition, so we called them inert. As you studied them further, under very strict and extenuating circumstances, you could get these to bond with very select atoms, so they changed the name from inert to noble gases. But just think of it, no reaction, noble gases, and inert. Okay? All right. Very good. Hopefully everyone's with me so far. Let's do the next thing. Let's go ahead and identify the different, what do we call them? The patterns. So the trends, the vertical or the horizontal trends. So let's go ahead with our first one. Let's start with periods, or what we would call rows. Now, I gave you a way to remember this. Think about writing a sentence. Writing a sentence, you go left to right, and you typically end it with a period. So periods and rows go left and right, okay? And if you look at the periodic table, when you guys do this, you're going to draw your little arrows right here. Everything in period 1 has one shell, okay? One energy level. So if you did atomic structure, Bohr's model, and you were drawing that, you would draw one shell for everything in column 1, and there's only going to be 2 elements in that. So that's going to be hydrogen and helium. So how many shells do the atoms have in period 2? Well, lithium, beryllium, boron, carbon, all the way to neon, they both have 2 shells because they're in period 2. If you're in period 3, you're going to have, you guessed it, 3 shells, and if you're in period 4, you're going to have 4 shells. This will go all the way down to 7, and that's the greatest number of shells you can have in atomic structure is 7 shells or 7 levels, okay? All right. Now, how about the one that goes up and down? Well, let's write that down. So that would be called families, groups. Sorry for the handwriting. I still have the broken hand, so it's not the best. Hopefully you can still read that. Families, groups, and columns. Now, I gave you something to remember this as well. I said life, just like families, have their ups and downs. If you have any siblings, you know what that life is about, right? Okay, so family, just like life, has their ups and downs. So families, groups, and columns go up and down. So I'm going to go ahead and look at family 1, which is 1A. We'll circle that. You guys are going to circle 2A, circle 3A, circle 4A. Anyone that has an A, not a B, but anyone that has an A, we're going to circle those. Why do we do that? Well, we'll put a circle right here. Circle equals valence electrons. Okay? And the valence electrons will determine chemical properties or reactivity. Yes, when you guys do this, I want this one written down. That is something kind of new that we're going to add, but it's really important, so I'm going to put a star there. So that means, let me get the pointer here, follow along guys, that means everything in family 1A has one electron on its final outer shell. So that means that they're all super, super reactive and unstable. Those are the alkali metals with the exception of hydrogen, that's a gas. Then everything in 2A, everything in family column group 2A, where I'm showing you, everything has two valence electrons on the last shell. These are excuse me. These are our alkaline earth metals. This is the alkali metals. This is the alkaline earth metals. Then you have your transition metals here in the middle. They do not follow an electron configuration pattern, so don't worry about that. That's why we skip them. That's why they have the B's on there. If you're in column 3A or 13, you're going to have three valence electrons in this family right here in this column. And same thing here, 4, 5, 6, 7. That's the other super reactive one, which would be halogens, okay? And then if you go to 8A, not the noble gases, non-reactive, then those all have a stable shell. They all have 8 on the last shell. The exception is helium, because helium doesn't need to have 8. Since it has an atomic number 2, you're only going to have 2 valence electrons. And how many fit on the first shell? 2. So it has a full shell. So everything in 8A has a full shell. They all have 8 with the exception of helium. I don't know if I said hydrogen, but helium has 2. Okay? So that's how you read the families, groups, and columns, as well as your periods and rows. Let's see, what else do we need to write on here? Okay, the next thing that I want you guys looking at, let's get a highlighter back. I want you guys to highlight the, oops, sorry. Let's highlight the atomic number, because when you look at the tiles, they actually give you quite of information that's really easy to understand. Oh, sorry. Let's not switching over. Let me try one more time. So we've got 14. So what does that atomic number tell us? That atomic number tells us the protons, and that atomic number tells us the electrons. So go ahead and put a plus and a minus. Now, this is an atom that hasn't bonded. So this is like a standard atom. Most of the time when they test you, this is relevant. So if we say it's silicon, which is showing here, and it's, you know, it's silicon because it has the symbol Si, it has the atomic number 14. Well, how many protons does it have? You don't have to do any math because you're writing the symbols down that I just showed you. That means it has 14 protons. Well, if I ask you, well, how many electrons does it have? Well, if it's a regular atom, that means it has 14 electrons. That means the protons and the electrons balance each other out and you'll have 0 total charge, right? 14 pluses, 14 negatives equals 0 total. Now, atomic mass, if you look at that one, that's the one with the decimal. That's the one you're going to round up. So how do we find neutrons? So let's go ahead and write this down. So neutrons, would be 28, and then you're going to round this one if you need to. But this one is 28.0, so we don't round it up. So it's 28 minus 14, and your answer is the number of neutrons, okay? So you need to write that down when you guys are marking up your table. That way you remember how to find neutrons. You take the atomic mass, which is the one with the decimal, and they're all given to you here on the table. You round it, so this one was 28.0. If that 0 was 5 or higher, it would be 29. Since it's less than 5, we don't round up and it stays 28. You take the atomic number, okay? Anytime you see the word mass, it's going to be the one with the decimal. So if they call it atomic number, mass number, it doesn't matter. If you see the word mass, then it's going to be the one with the decimal. Atomic number is the one that you see here. It's on top. And that's just going to be subtracted by the one with the decimal. Whatever you get is your number of neutrons. Okay? Good. Let's see what else. There are some trends that we need to write. Now, they don't fit here because I kind of wrote in the way. So I'm going to write the trends here at the bottom. So let's go ahead and draw a line like this. And some of the trends that you need to be aware of is decreasing. Write this down. Oh, sorry, this is really hard to write here at the bottom. So I'll do my best. Decreasing metallic properties. What that means is you have more metals and more properties of metals on the left-hand side, which you can see that. And as you move to the right-hand side, then you have your, when you get the highlighter or you get the pointer. So like in this area over here, these are all metals. So you have strong metallic properties in this side of the table on the left side. But as you go from this side over here, now you have the semi-metals, the semiconductors, the hybrids, the mutants. Those are your metalloids. And then if you go even further to the right, then you have your non-metals, which are not metals at all. So that's why you have decreasing metallic properties. More metals here. These are all your strong traditional metals here. And as you move across the table, you have less and less metallic properties. Okay, let's see. Is there anything else that I forgot? Something else you can add in there that is not necessary, but it'd be fun to add. Maybe you guys can do this just in case a question comes up. Put a little teardrop on mercury. That's my favorite element, as we know, but it's also the only liquid metal at room temperature. And you might want to circle sulfur. That's the yellow rock of not the non-metals. Okay, that's another really important one. They usually test you guys on that. I think this might be it. We'll do the triangles and the formulas on the back part of the chart. So what I need you guys to do now is review what I just wrote, make sure you understand it, and then you're going to practice it 3 to 4 times until you get 100% of what you see on here on your practice paper. So if you don't get it the first or second time, you keep going. And even if you do get it, it's good practice because you really just have to nail it one more time, and that's going to be for the test day. And after that, you can forget it if you want to until you get to chemistry because you don't need to remember it again. Okay, so I'm going to go to the next slide here. Let's go. Okay, now let's find out if you can actually use the periodic table as a tool to help you answer questions. You do not need to write anything for this, just follow along and see if you can answer the questions as I ask them. So, let's say you're doing the STAR test and it gives you lithium, it gives you aluminum, the question gives you fluorine, xenon, and bismuth. And the question says, which of these elements, and it's the ones I'm highlighting, chemically behaves or has the same chemical properties as phosphorus or a phosphorus atom, which is right here, okay? So that's how they kind of test you on these questions. So let me ask you, okay? Phosphorus right there, all right? Which behaves chemically like phosphorus? So what you are going to want to do for this is figure out which one has the same valence electrons as phosphorus. That would answer the question of how do they behave chemically, okay? So the first thing we're going to look at is lithium. Lithium has 1 valence electron. That's wrong. Aluminum has 3 valence electrons. That's wrong. Bismuth, it has 5 valence electrons. That is also in the same family or column as phosphorus. That would be the right answer. Fluorine has 7, so that's wrong. And then xenon has 8. So the correct answer for that first question, which one has chemical properties that are similar to phosphorus, would be bismuth because it's in the same family. So good. Let's try another one. Let me get a different color here. So let's use titanium. Let's use carbon, tin, selenium, helium, and let's say we'll go one more. Let's go mercury. Okay, ready? So if they give you a question where they're talking about, and they might just list them, they're not going to show you on the table. I'm just using the table because it's in front of me. If they say, hey, here's a list of all these elements, which one has the same level of energy shells, or which one is in the same period? Which two are in the same period or have the same energy levels? Well, the way you would do this is look at your periods and rows because that tells us our energy levels, okay? So if you want to pause the video real quick and see if you can answer this, go ahead. Okay, so which ones have the same shells or energy levels or in the same period? Well, helium only has one shell because it's in period one. Carbon has two because it's in period two. Titanium and selenium have four because they're in period four. Tin has one, or I'm sorry, five because it's in period five. And then mercury has six shells. So which one have the same? Well, the only ones that are in the same period would be titanium and selenium. So if you pick those two, then that would be your answer. Those two share the same shells or energy levels or in the same period. Okay? Okay, let's try another little question here. What if I asked you, let me highlight some elements here. I use green. So let's do carbon. Okay. Iodine. Let's go potassium, beryllium, and krypton, and zinc. Okay, ready guys? Let's try another question. Which of the elements that I highlighted, that I selected, has the greatest reactivity for a nonmetal? Again, which of the elements that I selected, that I narrowed down for y'all, has the greatest reactivity of a nonmetal? Well, the first thing you're going to want to do is eliminate the metals because those are not nonmetals, they're metals. So the first thing we can do, get rid of zinc, get rid of beryllium, get rid of potassium. Those are all metals. So now you're down to carbon, iodine, and krypton. But which one has the exploding marks to show us that it's ultra reactive and super unstable? Well, that would be iodine, right? We already know krypton has an X with a circle, meaning it's non-reactive, and carbon, the reactivity is not very much, because we never talk about it. So the correct answer, the most reactive nonmetal, would be iodine. Now, if the question said, what's the most reactive metal, then we would eliminate all these other ones, and we would go to the metal side, and that would be potassium, because that's in our 1A column with one valence electron. Okay, let's try another one here. Let me get another color. I'll use red. So which of these is the most chemically stable? In other words, the most least likely to react, the most chill, the most independent. So let's go calcium. Okay, let's go oxygen, helium, tungsten, um, nobelium, I think that's what that is, and iodine. So which of these is the most chemically stable? Which of these is the most non-reactive? Well, that if we're looking at chemical stability, that means that we are looking at valence electrons. So we're talking about chemical properties. We're talking about the word reactivity. That's why we got to write that down. So we always have that available to us. Which is the one with the full valence shell? The one that is the most stable. It doesn't need to bond with anybody. Well, we know calcium is not it. We know tungsten is not it. We know iodine is definitely not it. That's the most reactive. Oxygen is fairly reactive as well. That's not going to do it. So the answer is only one is a noble gas, and noble gases mean that they are inert, they don't react. So the answer would be helium. Hopefully you guys are understanding this and we're like, sir, we're ready. This is easy. Okay, let's try maybe one or two more questions on this slide, and then I think we got one more and we're done. Let's see. How about, okay, there is something I wanted to go over. So if you've kind of been drifting mentally, let's refocus because this one is something new, relatively new. I'm going to use a blue color here. Actually, you know what? I'm going to use green again. I guess I'll try the blue. All right, so I want to know which of these is the most chemically reactive? Okay, kind of a similar question. So again, which of these is the most chemically reactive, most unstable? All right. So let's go with cobalt. Okay, most reactive, unstable chemically. Let's go with um, magnesium. Okay, let's go with radon. Okay, let's go with neon. And let's go with chlorine. And I think that's all I want. Oh, well, let's go rubidium. So the question was, which of the ones that are in blue, not counting the metalloids, which of the ones in blue, okay, are the most reactive? No, let's take out rubidium. Which is the most reactive? And instead of rubidium, I'll replace it with hafnium. Okay, so which of the ones that I highlighted in blue are the most reactive? Okay, so we want to look again at reactivity. We're going to look at valence electrons. So that means we're going to look at the A's on top, right? So we know that neon is totally stable. So get rid of neon. We know that, actually, I'm going to take chlorine out of there. Okay, so we know that neon is the most reactive. We know that radon is also non-reactive. Okay, I don't know if I said that for neon, but we know they're both non-reactive. Um, Cobalt, we're not really entirely sure. It's a transition metal, so it's not very reactive. And then we know hafnium is also a transition metal. Those are also fairly stable. So that's going to leave us with the option of magnesium. I know what you're thinking, like, well, sir, that's 2A, that's not 1A. So here is a teachable moment, okay? I'm going to erase everything. So the answer was magnesium after I erased some that I forgot that I put in there. Okay, it's late, sorry. But let's leave magnesium. So let's take away the other ones, okay? So here is the new rule, or here's a rule that we haven't talked much about, but is very, very important, okay? So we know that 1A and 7A are the most reactive. What's the second most reactive group? Well, you have to make the number 8 again, right? So 2, which would be the next one in, 2A, is going to want to bond with which family? Well, 2 plus blank gives us 8. So 2 plus 6 gives us 8. So everything in 6A is actually going to be the next most reactive set of elements. So the first reactive set of elements is 1A and 7A, halogens and alkali metals. But after that, you move inwards, and what other combination can you get to make the magic number 8? Well, first it was 1 and 7. Those are the easiest way to make 8. The next easiest way to make 8 would be 2 and 6, because you can give your electrons away. The 2 electrons in 2A, you give them to 6A, it makes 8. So that means everything in 2A and everything in 6A are the second most reactive sets. So let me put this in perspective for you. We're just about done here, guys. Don't worry. If I said which one is more reactive in period 4, and it's potassium, and it's calcium, and it's gallium. If I wanted to know which is the most reactive from those three, it would be 1A is first, 2A is second most reactive, and then 3A is the next or the least most reactive of those three. Okay? So that's how this works. Now, what if I were to say, okay, well, what's the most reactive out of these three? Phosphorus, sulfur, and chlorine. Well, the most reactive would, of course, be 7A. The next most reactive would be what's in 6A, which would be sulfur. And then the least reactive of those three would be 5A. Okay, so don't get confused. The rule is fairly simple. 1A is always the most reactive. After that, 2A and 6A are the next most reactive groups. That's really all you need to know. And then everything else, They won't ask you about the reactivity because it's in the middle and it gets a little confusing. They'll ask you about reactivity for 1A, for 7A, for 2A, for 6A, and then of course for 8A. Okay, so hopefully that helps you guys remember how to find things on the periodic table based on valence electrons, based on reactivity, based on what family they belong in, and that will prepare you to use this as a tool as you go through your test, taking away all the stress and all the thinking. Let the table do it for you. All right, guys, last slide. Let's move forward. Don't forget, your protons give you the identity for all the elements. In this case, you have 1, 2, 3, 4, 5, 6. So you would have atomic number 6. 6 protons means you have a plus 6 charge for the nucleus. Why? Because you have 6 pluses. How many neutrons? 1, 2, 3, 4. There's 2 more in the back you're not going to see. Actually, those should be zeros because they have no charge. They're neutral. And so you should have 6 zeros, which would equal 0 charge for the neutrons. So the overall nucleus charge is a plus 6, right? It's always going to be positive. How about the electron cloud? Well, you have 1, 2, 3, 4, 5, 6. So you have -6 for the electron cloud total charge. Just remember, protons give the identity of the element, and the valence electrons, in this case, which are those, we should have 4 here, they give the reactivity or the properties. Moving on. Okay, so last thing we're doing is we're looking at our formula chart and we're looking at our triangles, making sure we can set those up. For the formula for density is going to be D and it's M over V, mass over volume. So when we look at our triangle, you'll see that mass is still over volume. Okay, nothing's changed. And then you have D over there in the corner. Now, if you forgot how to use this, I'm going to show you really fast. You cover whichever variable the question is asking for you to solve for. In other words, whatever you're looking for, that's what you cover. So let's try it out. So if you are searching for mass, then you use your thumb and you cover mass and obey what the triangle says to do. Density times volume. That's how it would give you mass. So whatever you're going to solve for, you cover, and then you go ahead and obey whatever the triangle tells you to do. Okay, so let's move on to average speed. So for average speed, it's the same thing. You have distance over time. Well, guess what? We still have distance over time. All right, again, let's just say you're solving for t, time. So you would cross out t in time, and you would just look at d divided by s. You put d for distance in the calculator first, divided by, and then you put the value for speed. That's going to give you your answer. You always want to obey the triangle. Don't try and overthink it. Just let the triangle do the work. Let the calculator do the work. Don't fight it. Okay, last one. This is the easiest one. Uh, Net force. Okay, force equals ma. In this case, let's say we were searching for mass. So what you would, or let's just say we were searching for acceleration. So you would cover this a, and you would be left with F divided by M. Okay, now let's use this rock for an example because this is the only part that might confuse y'all. So let's just say we have a rock here and we have 3 newtons and then we have 5 newtons going this way. So if you're searching for A, that means that we would cover that, right? So we need to know the value of F and we need to know the value of M. So we know the mass. They'll probably tell you, 2 grams or something, right? Okay, cool. So we know that. What about net force? Well, sir, there's 2 forces. Okay, you have to solve for net force to get your one number. So what do we do? If you remember back when we did this with unbalanced forces, okay, we have 3 going one way, 5 going the other way. Are they going in the same direction or are they going in different directions? If the answer is different, you subtract them. So you would do 5 minus 3, and your answer would be 2 newtons of force. And then so now you have your F, now you have your M, and you can go ahead and divide just like the triangle says. Okay? The one last thing about this that confuses a couple of people, I'm going to show you something, is always name the direction the arrows go because people get confused by that. So if I were to do 3 newtons and 6 newtons, and I asked you, do we add or subtract? Well, the way you can figure this out is just tell me which direction they're pointing. So if they point left, you're going to put L. If they point right, you're going to put R. Did you write the same letter? No, you didn't. So they're going in different directions. You can subtract. People get really confused, and I'll show you the example when they do this. And it's 4 newtons and 2 newtons. And people want to add these. Well, do what I just said. Which direction is this one pointing? It's pointing to the right. Which one is this one pointing? Well, it's pointing to the left. Okay, if you think they're pointing in the same direction, did we write the same letter? No, we wrote R and L because one's pointing right, one's pointing left. Therefore, you would still have to subtract them, and that would give you your net force. Okay, guys, good luck on your STAR test. It should be tomorrow if you're watching this video the night before. I'll be praying for y'all. Just watch all the videos you can, do all the practice, study your dyno notes, and get a good night's rest, and we'll live with the results. I'm sorry I'm not there with you guys. It's not my choice. I miss y'all very much, and I wish I could be there with y'all, but make me proud either way. Okay, just do your best, and we'll live with the results. We'll see you guys later. Bye.